In chemistry, the valence of an element is a measure of its combining power with other atoms when it forms chemical compounds or molecules. The concept of valence was developed in the last half of the 19th century and was successful in explaining the molecular structure of many organic compounds. The quest for the underlying causes of valence lead to the modern theories of chemical bonding, including Lewis structures, valence bond theory, molecular orbitals, valence shell electron pair repulsion theory and all the advanced methods of quantum chemistry. The combining power or affinity of an atom of an element was determined by the number of hydrogen atoms that it combined with. In methane, carbon has a valence of 4. In ammonia, nitrogen has a valence of 3. In water, oxygen has a valence of 2. And in hydrogen chloride, chlorine has a valence of 1. Chlorine, as it has a valence of 1, can be substituted for hydrogen, so phosphorus has a valence of 5 in phosphorus pentachloride, PCl5. Valence diagrams of a compound represent the connectivity of the elements. Lines between two elements, sometimes called bonds, represented a saturated valency for each element. Examples are, valence only describes connectivity, it does not describe the geometry of molecular compounds, or what are now known to be ionic compounds or giant covalent structures. The line between atoms does not represent a pair of electrons as it does in Lewis diagrams. Modern definitions, valence is defined by the IUPAC as the maximum number of univalent atoms that may combine with an atom of the element under consideration, or with a fragment, or for which an atom of this element can be substituted. An alternative modern description is, the number of hydrogen atoms that can combine with an element in a binary hydride or twice the number of oxygen atoms combining with an element in its oxide or oxides. This definition differs from the IUPAC definition as an element can be said to have more than one valence. History. The etymology of the word valence traces back to 1425, meaning extract, preparation, from Latin valentia strength, capacity, and the chemical meaning referring to the combining power of an element is recorded from 1884, from German Valence. In 1789, William Higgins published views on what he called combinations of ultimate particles, which foreshadowed the concept of valency bonds. If, for example, according to Higgins, the force between the ultimate particle of oxygen and the ultimate particle of nitrogen were 6, then the strength of the force would be divided accordingly, and likewise for the other combinations of ultimate particles. The exact inception, however, of the theory of chemical valences can be traced to an 1852 paper by Edward Frankland, in which he combined the older theories of free radicals and a OE-type theory with thoughts on chemical affinity to show that certain elements have the tendency to combine with other elements to form compounds containing 3, that is in the 3-atom groups, or 5, that is in the 5-atom groups, equivalents of the attached elements. It is in this manner, according to Frankland, that their affinities are best satisfied. Following these examples and postulates, Frankland declares how obvious it is that, this E combining power was afterwards called quintivalence or valency. Common valences, for elements in the main groups of the periodic table, the valence can vary between 1 and 7. Many elements have a common valence related to their position in the periodic table, and nowadays this is rationalized by the octet rule. The prefixes uni mono, db, triter, quadritetra, pentaquinque were both used by different writers. Polyvalence or multivalence refers to species that are not restricted to a distinct number of valence bonds. For example, the CS plus cation is a univalent or monovalent cation, whereas the Ca2 plus cation is a divalent or polyvalent or multivalent cation, and the Fe3 plus cation is a trivalent or polyvalent or multivalent cation. As a result, examples of polyvalent cations include the Ca2 plus cation and the Fe3 plus cation. Valence versus oxidation state. Because of the ambiguity of the term valence, nowadays other notations are used in practice. Beside the system of oxidation numbers as used in stock nomenclature for coordination compounds, and the lambda notation, as used in the IUPAC nomenclature of inorganic chemistry, oxidation state is a more clear indication of the electronic state of atoms in a molecule. The oxidation state of an atom in a molecule gives the number of valence electrons it has gained or lost. In contrast to the valency number, the oxidation state can be positive or negative. Elements in a high oxidation state can have a valence higher than 4. For example, in perchlorates, chlorine has 7 valence bonds and ruthenium, in the +8 oxidation state, and ruthenium tetroxide, has 8 valence bonds. Examples: valences according to the number of valence bonds definition and conform oxidation states. The univalent perchlorate ion has valence 1. Iron oxide appears in a crystal structure, so no typical molecule can be identified. In ferrous oxide, Fe has oxidation number 2, in ferric oxide, oxidation number 3. Examples where valences and oxidation states differ due to bonds between identical atoms. Valences may also be different from absolute values of oxidation states due to different polarity of bonds. For example, in dichloromethane, CH2Cl2, carbon has valence 4 but oxidation state 0. Maximum number of bonds definition. Franklin took the view that the valence of an element was a single value that corresponded to the maximum value observed. The number of unused valences on atoms of what are now called the p-block elements is generally even, and Franklin suggested that the unused valences saturated one another. For example, nitrogen has a maximum valence of 5, in forming ammonia 2 valences are left unattached. Sulfur has a maximum valence of 6, in forming hydrogen sulfide 4 valences are left unattached. The International Union of Pure and Applied Chemistry has made several attempts to arrive at an unambiguous definition of valence. The current version, adopted in 1994, the maximum number of univalent atoms that may combine with an atom of the element under consideration, or with a fragment, or for which an atom of this element can be substituted. Hydrogen and chlorine were originally used as examples of univalent atoms, because of their nature to form only one single bond. Hydrogen has only one valence electron and can form only one bond with an atom that has an incomplete outer shell. Chlorine has 7 valence electrons and can form only one bond with an atom that donates a valence electron to complete chlorine's outer shell. However, chlorine can also have oxidation states from +1 to +7 and can form more than one bond by donating valence electrons. Although hydrogen has only one valence electron, it can form bonds with more than one atom in hypervalent bonds. In the bifluoride ion, HF2, for example, it forms a 3-center 4-electron bond with 2 fluoride atoms. Another example is the 3-center 2-electron bond in diboron. Maximum valences of the elements. Maximum valences for the elements are based on the data from list of oxidation states of the elements. Covalence. The term covalence is attributed to Irving Langmuir. He stated that the number of pairs of electrons which any given atom shares with the adjacent atoms is called the covalence of that atom. The prefix co means together, so that a covalent bond means that the atoms share valence. Subsequent to this, it is now more common to speak of covalent bonds rather than valence, which has fallen out of use in higher-level work with the advances in the theory of chemical bonding, but is still widely used in elementary studies where it provides a heuristic introduction to the subject. See also, valence electron, Abeg's rule, oxidation state, references.